Yes. Okay, good evening, everyone, and good morning, Dr. Sina. Thank you for coming. And okay, so welcome again to the International Virtual Course, Geophysics for Engineering and Environment, from Theory to Practical Application. And this course is coordinated by Pak Wahyudi, Dr. Wahyudi Widiatmoko, and I am Harmita Lestari as a chairman for this session. And now we are in the session 2 of the day 7 of IVC. And the topic for this session is a soil stabilization process using biogen and its monitoring using geophysical method. And the lecturer is Dr. Sina Seniam from University of Oklahoma, USA. So Dr. Sina, how are you today?
I'm good, thanks. Everything is all right around here.
Thank you. So you have about 1 hour and 35 minutes to deliver your lecture and continue with the question and answer session. So you can start now. Time is yours.
Thank
Please,
you.
Share your presentation. Oh, I'm sorry. I will read your CV first. So let me share my screen. I'm sorry. Okay, everyone. Dr. Sina Senihan from University of Oklahoma, USA, and the education and qualification, bachelor from University of Tehran, Iran, and master degree from Sahreb University of Technology, Iran, and doctoral from Rutgers University, New York. And the position now is assistant professor at University of Oklahoma. Previous publication, over 25 publication on ResearchGate and over 97 citations. Skills and expertise, near surface geophysics, environmental geophysics, engineering geophysics, soil mechanism, biogeographics, hydrogeographics, and computational geophysics. The latest projects, data modeling and inversion software for electrical resistivity and induced polarization, core developer, REST IPYE multi-platform software for interesting and modeling ERT and up geophysical data in 2D and or 3D space, and SIPY spectral induced polarization, SIP data analyzed with GUI, and one-dimensional call and deep by decomposition inversion including complex conductivity signatures of unconfined compression deformation and shear failure in soils, and complex conductivity signatures of microbial-induced calcite precipitation field and laboratory scales. So, Dr. Sina, time is yours now. Please share your screen and presentation.
I want to do that, but it says host disable share screen, so I can't do it.
Okay, wait.
Okay, now I can.
Okay.
Great, thank you very much. Just to confirm, do you see my screen?
Yes, clearly.
Great. All right, let me start. So first of all, thanks for inviting me here. I'm really glad to be talking about my past projects as well as the theory and applications of geophysics, specifically geoelectrical methods for soil stabilization, and probably slightly more after that about soil deformation in general. So I would say my project so far work around engineering applications of soil being stabilized all the way until we monitor it to be destructed, either by natural phenomena such as heavy rain or by the weight of building or something like that. So I start from the very beginning, how to stabilize loose soil, and we'll continue all the way to show you how we use geophysics to monitor soils that are prone to be failed. First of all, thank you for the CV. I'm not gonna talk much about myself anymore. If you want to know more about me, please scan this QR code on this slide. It directs you to my website. I got my bachelor's in mining engineering in 2011, and then continued as becoming a petroleum engineer as a master's student in 2014. But by that time, I realized these two are actually contaminating and the environment and very problematic. So I pursued a PhD in environmental geophysics to know more about environment, how to protect it, and so on and so forth. I have done a lot of field work in the United States and outside, and was a part of a team to develop a few software for geophysical data analysis that are available on internet that you can freely download and use for your projects. In this talk, I'm going to talk in two parts. The first part would be basically my PhD project, which was the soil stabilization involving an environmental friendly method called microbial induced calcite precipitation. And then I will talk about how I approach to monitor it, unlike the regular and conventional methods that basically take a direct sample from the soil or analyze it. I use geophysics to indirectly monitor it and make sure I don't disturb anything that's in the subsurface. In the second part, I will talk about how we try to use the same geophysical method to study the soil failure. So we know after soil has been stabilized, it can become destabilized by a lot of phenomena such as rain, such as buildings and infrastructure, and a lot of features. So we must know if our geophysical method is capable of doing both, monitoring soil stabilization as well as its destruction, because we want to prove that this geophysical method that we are talking about is a proper method for long-term monitoring a site that has been stabilized before. But first, let's talk about the importance of soil in our life. We all know that soil is the first point of contact to the ground, our earth that we live on, and it supports our ecosystem. All of our environmental interactions are through the soil. Our agriculture comes from the soil. Raw material mostly come from the soil. And also our physical and cultural heritage, our history is buried in the soil. But most important of all, I would say, is infrastructure. Soil is the first point of contact for us. So we have to know that the soil that we are trying to build our buildings, roads, and everything is able to support these infrastructure. To do so, we have to do a lot of analysis to make sure that soil is capable of staying stable throughout the time. Because if it's not stable, we may have a house that collapses because of a landslide. We may have a levee that is actually gonna collapse, and a lot of bad events can occur if we don't study the soil fair enough to know its mechanical properties. Rain, earthquake, weathering, and even anthropogenic activities all can make soil to become unstable. And as you know, we cannot live on an unstable soil. So the objective here for me and for us geophysicists is to know if our methods are able to monitor the process that we use to stabilize the soil or not. And can we use the method to identify these mechanical properties of soil with geophysics, and hopefully in future, by the permanent site installation of such geophysical methods, we were able to kind of predict the mechanical problems that may occur in the future, basically say when or if the soil is going to fail because of any of these unstabilizing events such as rain. So let's talk about soil stabilization and geophysics. The process of soil stabilization or soil strengthening or ground improvement, as civil engineers would call it, is basically used for a lot of different factors, such as building foundations. You cannot build any buildings on a loose soil. You cannot build a house on sand. So you have to make it to become stabilized. Now, this is not the only thing that we use as stabilization. We have a lot of desert areas. We do stabilize the soil because of preventing the erosion as well as dust control. And sometimes there are rocks that are actually prone to become unstable, and we can use crack remediation and the permeability reduction and so on with these soil stabilization methods as well. Now, common methods that are currently in practice that civil engineers use are a lot of methods, but most of them involve injecting an agent into the subsurface that binds these loose material together and stabilizes the soil. As you can see in these pictures, I'm showing here the first method is the simplest method, pouring a cement slurry on the soil, and that basically binds everything together and that soil becomes stable. Now, the problem with such a method is that, as you can see, it destroyed everything, all the vegetations, all the environment, ecosystem, and everything. And as you probably guessed, it is not a cost-effective method because look at the instrument they're using, the material they're using, and so on. The other methods that may be not as destructive on the surface would be injecting the cement through boreholes into the subsurface. Although this method might be more effective than just pouring the cement, again, this is not a cost-effective method because we have to drill a lot of small boreholes. And also, both of these methods are using a man-made chemical material that is not environmental friendly. And because it doesn't have any agent in subsurface that can move around, basically, we inject everything through boreholes or pouring it on surface with the mechanical force from us humans. We cannot control its distribution in subsurface unless we inject so much that become financially not feasible. Now, these problems can be overcome with a new method. This method is called microbial induced carbonate or calcite precipitation. What we're using here is using the microbes that are already in the soil. They're available everywhere. They are not harmful to us humans, and all they need is a little bit of food, a little bit of ingredients, and they will produce this binding agent for us in the subsurface. In here, this binding agent, this cementation agent, is calcite, a mineral that we find it naturally occurring as a cementation agent in a lot of sedimentary rocks. We try to harness this feature in our benefit and make the soil stabilized with these microbes without disturbing the environment. As you can see in the bottom image in here, you are clearly seeing that in the site that I was there and MICP was used, all the vegetations remained intact. We didn't have to remove anything. And in the future slides, I'm going to show you actually that project was successful. So this method, compared to the conventional methods, is environmental friendly. As a naturally occurring material, calcite is not harmful to the environment. It is relatively low cost. We're not injecting through too many boreholes or too much material. It is much easier to achieve a homogeneous spatial distribution because you're using the microbes as an agents in subsurface, and they're tiny. They can go to all of these small porous spaces and produce calcite over there, and we don't have to do anything except feeding them. So the only thing that remains that do we know it is good for long term or not? So that's why we are using geophysics to make sure this method is viable for long-term use, such as previous methods of injecting cement into the subsurface. A little bit about the monitoring techniques that we can use for monitoring this project. As you geophysicists already know, there are two ways: direct measurements. Basically, a lot of engineers use this method. They drill boreholes or take an actual sample from the stabilized soil in the subsurface or on the surface. These methods are accurate. You're basically taking out a sample that has been stabilized, taking it to the lab, do a lot of analysis such as mechanical properties, triaxial test, confined stress test, and so on, and make sure that soil is working. Now, the problem with these methods is that they are discrete. So the sample that you're taking belongs to the point that you took it. It's not representing the rest of the area that was stabilized. And if you want to make sure that the whole area is stabilized, you have to take a lot of samples. And basically that defeats the purpose of stabilizing, right? You're destroying the site that you just stabilized. And it is expensive if you want to apply, take a lot of samples, and it's time delayed. Most of the times the sample has to go into a lab, get analyzed, and then the data comes back. So time has passed, and we don't have such luxury when we are working on a project that has a deadline. On the other hand, are the geophysical methods. These methods, most of the times, we do not need to dig any boreholes. Basically, they provide the spatiotemporally rich information about the subsurface with a few sensors that are laid on the surface of the ground, and they can be super cost effective compared to the direct sampling because we're not destroying anything, and we can cover a large area in a short amount of time. In addition, they are very beneficial for automation. We can use geophysics basically permanently at a site and continue collecting data forever. If we have the right tools, software that I'm going to talk about at the end of this talk, we can analyze data on the go and get information about what's happening in the subsurface during soil stabilization without any problem. Now, there are some cons to these as well. They usually require ground truthing, so we cannot just take our instrument in the field without any prior knowledge of the site and pinpoint what exactly is going on in the subsurface chemically or physically. We can say something is going on, but we can't exactly say what that is. So we need a little bit of information, maybe a little bit of boreholes, a few ones here and there, and then we can just basically compare that with data that we found on geophysical analysis. In here, I used mostly geoelectrical measurements for both of these projects of soil stabilization and mechanical properties monitoring. In general, what we do, basically, we inject a current into the subsurface through a range of electrodes, and we measure the potential differences, the time delay that these potential measurements take them to be measured, as well as the redistribution of ions because of this current that was injected into the subsurface. Basically, if we want to put it as simple as possible, we will have a battery, an ammeter to measure the current, and a voltmeter to measure the potential. We inject the current with the battery through the current electrodes, positive and negative. What happens? The current travels through the subsurface, and that causes a potential difference from this point to this point. And we can measure that through our potential electrodes. Another thing that occurs is that because ground actually, or subsurface, is not a conductive material such as a copper wire, it causes the ions to be redistributed and the ground acts as a capacitor. So current passes through the subsurface, and also a capacitor acts in there. So we can measure both resistivity, or basically the ability that causes the voltage to drop, and polarization of that redistributed ions because of the diffusions that occur in the subsurface. If I want to put it in a context, basically when we inject the current into ground material, let's say soil, as you can see in here, what happens, the current travels in two pathways. One, through the pore-filling fluids in the interconnected pores. So the current passes through them because the ions transferring the charge, as well as on the surface of the minerals or the soil grains. Now, if we have an isolated pore space, basically the current can't get through that. So we need interconnected space to make sure it's working. Now, if we focus more on the surface of the minerals or the soil grains, we are able to see that the soil grains are not conductive, such as a wire. So basically what happens, they get polarized. They get polarized because they're negatively charged. We are passing through a current, so positive ions get attracted to the mineral, and then the free fluid acts as a connector of the current. And these two layers that we call them the electrical double layer, fixed stern layer and diffuse layer, act as that leaky capacitor or that capacitance, the basically polarization. This allows us to measure a geophysical signal called complex conductivity. This frequency-dependent measurement gives us a lot of information about ions and redistribution of pores and so on in the soil. It allows us to measure at the same time both resistivity and polarization in the subsurface through this equation. So if we simplify everything, we have the complex conductivity, which is a frequency-dependent measure. So basically it depends on the frequency that you inject. If you inject at 60 hertz, like the current that we have in our outlets, you have a different signal than if you inject at 2 hertz, for instance. It will essentially give you the conduction through the electrolytes, as well as polarization that is happening on the surface of the minerals, or let's say at the electrical double layer close to the surface of the mineral. Based on that, we are able to measure a lot of different features because electrical conduction through the pore filling fluid depends on the saturation. If we have a partially saturated soil sample, we have a different conduction. If we have a dry sample, a different conduction. And if it's fully saturated, a different conduction. It depends on the porosity. The more porous it is, the more interconnected the space that we have, the better conduction, as well as depending on the fluid conductivity, if you have a very saline solution or not a saline solution, and so on. So basically the ionic concentration is important as well. Now, the surface conductivity, basically the polarization that was happening in here, the redistribution of ions in the double layer, depends on the surface area and not only saturation. Basically, the more grains you have and the finer they are, you have more polarization. You have more surface area to get polarized, more surface ions. And then in that surface area, if the ions are bound as they are and they're not mobile that much, you can actually measure that as well. So the ionic mobility also affects the surface conduction and the polarization as well. There are other factors such as pore size distribution, very important. If you have a larger pore, it takes for the ions to distribute slower because they need to travel a longer distance, as well as if they are smaller, so a shorter distance. So basically the polarization occurs in a shorter time. And the interfacial charge density, basically the amount of these positive ions that are going into the electrical double layer. What happens with the complex conductivity, or basically spectral induced polarization, because we're measuring the induced polarization over a range of frequencies, is that we are injecting the current at a different frequency. In here, just shown one frequency, right? And what it causes is the ions to become polarized. Now, as this current is changing its polarity, the ions tend to get redistributed. And because ions take time to get redistributed, we will see something called a phase lag. This time difference can give us something called a phase lag. Basically, during measuring the potential, we will see everything with a time difference. We know the current that injected, how much amperage we injected, and how much voltage was that. So basically, we also get the impedance, or the complex conductivity measure of the resistance. Combining these two will give us complex conductivity. Now, for doing that, we need a factor called geometric factor to know exactly how we distributed our electrodes on the surface or in subsurface or on sample, or basically know the geometry of our measurement sample. And based on that, we can get the real conductivity, which is the conduction, for instance, through the pore filling fluid, and the polarization, which is the energy storage because the ions were redistributed and got polarized. We get these two in both lab settings and field setting. For the lab measurements, we usually do everything on a column of soil. So we have an instrument capable of injecting current at multiple frequencies. We usually have a current electrode at bottom and a current electrode at top of this column that is packed with soil sample, and two potential electrodes in the middle. The geometric factor for such a column is very easy to calculate, is basically the area over length. And based on that, we can calculate the complex conductivity measures. Sorry. So what it will give you, you start measuring through from lower to higher frequencies, and each of them will give you a point of phase and impedance. And when you plot everything over a frequency range of your measurements, you will get such a diagram. So ideally, you will have a peak in your phase shift or phase lag spectra, and sort of an inverse S shape in your impedance. So as I said, you will be measuring a phase lag, which is basically inverse tangent of the imaginary part, or the energy loss, energy storage over the conduction or real conductivity or energy loss, which because at the lower frequencies, these are very different than each other, we can just ignore the tangents, or simply put, the phase would become the imaginary conductivity over the real conductivity. And it is measured in radians, but in reality, for environmental applications, that's much smaller than radians, and we get milliradian range. Then we have the impedance, which is the potential difference measured at these two poles, these two potential electrodes, for instance, and the magnitude of the injected current will give you the impedance. Combining them with the geometric factor, which can be very complicated if you have an array of electrodes on the surface, but it's super easy for a column, which is area over length, will give you the complex conductivity magnitude. Now, to convert this to real and imaginary part, we will use these two equations because it's a complex number. It has an imaginary part and a real part. The imaginary part would be this equation. So the square root of real conductivity, the squared real conductivity plus the squared imaginary conductivity multiplied by cosine of the phase lag. And the imaginary part is the sine, the same thing, so the magnitude by the sine of the phase lag. So this is the imaginary part and this is the real part. And then we can use these different measures for different applications. So as you remember, the imaginary part represented the energy storage or the polarization. It depends on the surface area, on the pore size distribution, and so on. And the real conductivity depended on the saturation, porosity, and the salinity. So we get different properties from the subsurface or our sample with this complex conductivity method. In the field, we use the same exact thing, but we have a number of electrodes and array in form of an array. Now, simply put, we will be having 4 electrodes at each time we are measuring this, and then we are combining all these 4 electrode measurements together and make a map of subsurface, either in 2D or 3D. If the electrodes are arranged in a grid, such as this picture, we will get a 3D image of subsurface. If they are in a line only, we will be getting a 2D or a cross-section of subsurface. A lot of instruments are available to do so. Most of them are working based on resistivity and time domain induced polarization. And they are usually incapable of doing multi-frequency injections in the field. Those that are available to do multi-frequency injections in the field are very expensive, but scientists have shown that time domain measurements can actually be converted to frequency-dependent measurements as well, only if we get the full waveform of our injection. So we know the whole story, let's say, which I'm going to tell you about. Now, in time domain measurements, what we are doing, unlike the frequency-dependent measurements that we were injecting an alternating current, we are injecting a direct current into subsurface. What we do, we basically turn on the current in a positive polarity, turn it off, and then turn it off in a negative polarity. And keep doing that. It's kind of replicating the same thing with the alternate, but in a DC, the direct current manner. And for the ions in the subsurface, same thing happens. They get polarized again because they need time to get redistributed around a grain, such as this one, right? So when you inject the current, what happens is that it takes time for the voltage to get to its maximum. This kind of curve has been exaggerated in here, but that's what happens in reality. This is showing you the time that it took for the ions to get redistributed. So that's why we call it time domain, because we are measuring everything over time. Now, when you shut off the current, again, for the ions to go back to their initial position before being polarized, there is a time too. And that causes a measurable voltage signal. We keep doing that, and we're basically measuring a different time window, different time windows on that curve when we are shutting off the current and measuring some parameter called chargeability. So chargeability is a time domain sort of complex conductivity measure. Can be converted easily to phase lag. Now, in practice, in theory, what we are aiming for is measuring the whole waveform from the moment that we're shutting off the current all the way until it goes to voltage 0. And then if we measure the whole area under this curve, we are able to measure the chargeability. That's what we call the full, why we need a full waveform. Most of the instruments, unfortunately, do not measure a full waveform. What they do, they are measuring different slices in here and basically averaging out the measurements over there. And instead of calculating this, the integral, they are kind of just measuring an average of each of these measurements in points that they're measuring on this curve. Now, most of the instruments do that because when you shut off the current, there is a lot of noise in here. It's not as perfect as you see in here. And they don't want that in their signal, causing a lot of error. And also, it's not so easy to basically measure that the moment you turn off the signal. But now the industry has developed, and there are a few instruments capable of doing a full waveform measurements for induced polarization. And basically, if you have the full waveform, you can easily convert it with Fourier transform into a multi-frequency measurement. Another method that I will be talking about in this lecture would be shear wave velocity. This is an accepted standard method for civil engineers to measure the stiffness of the soil. Basically, there is a question, I guess. No, sorry about that. So what it does is basically we are measuring the soil physical material inside the soil, and the more physical material we have, the better. Shear wave velocity only goes through the physical, the solid particles. It does not go through air or solutions. Now, for stabilized soil, we are injecting or we are adding more physical stuff as a cementation agent. So we are increasing its stiffness. We are adding more solid particles. So the shear wave velocity will be faster in that. So this is a direct measure of soil stiffness. We do that basically by passing through the shear wave into the soil and measuring shear modulus. And that in the lab, we are using something called a bender element. These are piezo ceramic material that, such as quartz, for instance, that when the current is applied on them, they sort of, their crystalline structure changes. So they kind of bend in this manner, if we want to put it. So we have two layers that are at different polarities. And what happens when the current is at positive side, one of them shrinks, one of them expands, causing the bender element to kind of go upward. And then if we change the polarity of the current, it goes down. What happens is if we alternate in this current, it sort of goes up and down, and produces a physical movement in that bender element, causes a shear wave to start propagating into our soil sample. Now, this piezo ceramic material have the ability to change to also produce current if they are they are subject to physical stress. So in the lab, we have one piezo ceramic bender element that is producing shear wave, and the other one at the other end, for instance, is receiving this shear wave. The shear wave reaches to this at a different time, and then basically causes the receiver to bend because of that wave, and then that can be translated into a current signal. We measure the time difference from the shear wave velocity that was started from this point and received at this point, and we know the distance, so we can easily calculate the velocity of the shear wave. We know the density of the soil that we have most of the time, right? And then we can calculate the shear modulus and soil stiffness. Now, this would be sort of a ground truthing engineering method for my geoelectrical measurements in the field, in addition to direct sampling. But before using the microbial approach, I have to see if my geoelectrical measurements are actually sensitive to the cementation agent, the calcite, right? Do I even get any signal if I have calcite? If I don't see any geoelectrical signal, if I have calcite in the soil, then what's the point? To do so, I did a controlled environment laboratory experiment in which I only use calcite, no microbes, no nothing. So I basically injected calcite powder inside my sample and measured its geoelectrical and shear wave velocity response to see if actually calcite has any effects on our geoelectrical and geophysical basically signal or not. To do so, we injected two different solutions, one calcium rich, one carbonate rich, and eventually calcite was precipitated inside our column. In the middle, we had both electrical electrodes on the sample holder as well as bender elements in the middle, and we were able to see that actually calcite was precipitated inside the column after about like 250 hours of experiment, something like that. we basically destructed the sample, took the soil and put it under the SEM microscopy, and we're able to see the control sample that did not have any calcite in it, basically did not have the carbonate solution in it and only the calcium-rich solution in it, showed no evidence of precipitation in between the grains or on the surface of the grains. But the one that had the carbonate, we will see the cementation in between soil grains, as well as the evidence of the precipitation on the surface of the quartz grains. You can clearly see the rhombohedral calcite crystals in here under the microscope. And also we were able to see if when we were destroying the sample, basically everything remained intact. So the mini borehole, I would say, that we dug did not collapse on its own because the soil was stabilized in there. Our ground truthing engineering accepted geophysical method showed that the soil stiffness has been increased. We saw a 33% increase the shear wave velocity, so meaning that we have actually filled the pores with solid particles, making the shear wave to propagate faster. As then that showed us the calcite actually cemented the grains. But what we were interested in was the complex conductivity method, or the geoelectrical response. In that, we were able to see a peak forming in our imaginary conductivity spectra. You remember that the phases I showed you, that we were looking for a peak, right? So we didn't have any peaks initially, but as the precipitation continued, we were able to see a peak is forming at around 1 hertz and keeps going up in the magnitude until the middle of the experiment, and it basically starts to go down and reaches to a constant level. Now, if you remember, I said that the imaginary part, the polarization part, the energy storage part depends on the surface area and the size of the pores and such factors. That basically tells you the more solid particles in a finer form you have, the higher polarization you get. Now, I interpret it that, all right, initially the signal is going up because the calcite is precipitating in a powder form. And now, as we keep precipitating, these powders are coagulating, and that initial increased surface area because of the powder form is actually decreasing because these are coagulating. They are connecting together and becoming larger calcite crystals, calcite coagulations. So basically what happens is that the surface area is reducing now from that peak after a few days and reaches to a kind of constant level, showing us that the calcite is no longer precipitating, like increasing in surface area inside the pore spaces. All it's happening either is probably the equilibrium, but basically the same amount is getting precipitated as the same amount that's getting flushed out or dissolved in the water, or basically the area in the middle that we were measuring in here is now fully saturated with precipitated calcite, and we are not sensitive to any area around here outside of these potential electrodes. So if the calcite is precipitating in here, we don't know it, honestly. So to basically put it in context, we had two different methods showing that our calcite precipitated soil stabilization method that was man-made sort of thing is effective, and also we can measure all of its geophysical signature. Either being the shear wave velocity, which showed an increasing trend over time, no going down, and the complex conductivity that showed the pattern of the precipitation as well. Not just showing that, okay, we have a stabilized soil, but it also showed us when it's the time to stop injecting calcite. We don't need any more material. This is very beneficial for field applications that makes us, okay, enough. We don't need more. We don't need to pay more money to inject more material. because now we reach the constant level of a stabilized soil. We're no longer stabilizing our environment. We're just basically flushing the stuff out. Initially, as I said, we assumed that we have a powder precipitation increase in the complex conductivity magnitude signal, and then these coagulated and created layers of calcite on top of each other, so that initial surface area that was because of the powder is reduced now. And then we reach to a constant level because of this equilibrium going on. This is very beneficial, actually, this equilibrium, because not only it tells you stop, if you have this geophysical complex conductivity method installed at a site permanently and actively monitoring the signal, if this goes down, we know something is wrong, right? So meaning that the site needs maintenance, and we have to get out and go and inject more material and stabilize the soil. So that actually is really good to know if anything wrong has happened to the site over time or not. For instance, if the rain kind of acid rain happened and washed away calcite or not. But one might say, okay, this is perfect. Why don't we just use this abiotic injection of two chemicals in subsurface and say, oh, we're good. Calcite is environmental friendly, unlike the Portland cement, for instance, and it works fine. Your geophysical signals work fine, but why do you need this? So to those people, I would say, all right, remember, if it doesn't have any agent for us in subsurface, to take this cementation agent with it and precipitate it in the smallest pores, then we're gonna get a pore distribution of cementation. Basically, whatever is happening is at the zone that we are mixing these two chemicals, at the zone we inject, not everywhere else. So how do we overcome that? To overcome this problem, we're gonna use microbes. Specifically, for the lab experiment, we are using a type of microbe called Sporcina pasteurii. These microbes are known to produce large calcite crystals, and they're very active in decomposing the material to produce calcite compared to the other communities in the subsurface. But we are just using these because we are using a lab measurement for here. In the field, we don't really need this type of microbe. All other type of microbes capable of precipitating calcite is going to work, which I'm going to talk about. In the lab environment, what I did was basically grew this microbes on a petri dish, and so we used the petri dish, and I forgot the name for it. I'm not a microbiologist, but this media, the growth media on the petri dish, for instance, in here that you can see, prevents the microbes from moving. So when you try to grow them, they do not go outside of the area that you put the microbes. So basically, we prevent them from moving so they don't become contaminated by other microbes. Or if there is any contamination, we can actually see that. So every step for using microbial project is to grow the microbes in isolated colonies to make sure you haven't done anything wrong. And then when we are sure that our communities are perfect and without any contamination, it's the time to move them from the solid state into liquids, because we want them to actually move in subsurface or in our sample. We don't want them to be at the fixed position, right? So what we do, we make a liquid growth media, and we basically take a little bit with a small spoon, I would say, a loop, and put it in there. And after 48 hours, they kind of occupy the whole thing, and they proliferate, and they can easily move. And then we can inject this solution into our column and start precipitating calcite, provided the right ingredient. So what are the right ingredients? These microbes need urea because they are capable of decomposing urea as a source of food for themselves. And when they do that, they produce carbonate. Now, if we have a rich environment that has calcium in it, it basically immediately starts precipitating calcite. So we're good here. But there is a benefit to these microbes as well. They tend to attach to this calcium ions. The calciums actually get attached to the body of these microbes. So as they move around inside the column to precipitate calcium, to find food, to basically go around and eat because they're hungry, they take these calcium ions with them, and wherever they go, they decompose urea because they're hungry, they produce carbonate, and at the same time, calcite gets precipitated. So we have a better distribution of the cementation inside our sample or under the ground using these moving microbes. We call them motile microbes. So compared to the previous method, we using the same injection ports like the previous time, but we are getting a better distribution of cementation inside our column. Or at least what we're hoping for theoretically. Let's see if we have reached to that point or not. In this part of the experiment, again, we use shear wave velocity as a ground truthing method. And we were able to show that the shear wave velocity increased about 34%, slightly more, but in the same ballpark as the previous experiment. Again, we are just using calcite inside our column, and then the benderemals are at the same location and so on. But clearly it shows us the calcite cemented the grains together. So microbial induced calcite precipitation works as a soil stabilization method. Geochemistry also proved it. We were unable this time to use SEM microscopy, so we did XRD instead. So we took our samples and put them under XRD, and were able that the untreated soil did not have any evidence of calcite in it compared to the treated soil. After 380 hours, we were clearly seeing a peak around 29 degrees, which is the time that the degree that we see calcite crystals. So we clearly have calcite precipitated, and also analyzing the effluent solutions at each step of the way, we were able to see that the concentrations of ammonia is increasing. If I go back here, you see ammonia is a byproduct of decomposing urea. So when it is there, meaning that the microbes did their job. They basically consumed the urea, produced carbonate, and released ammonia. So that's one of the good indicators that the microbes did their job. And ammonia is very stinky, it smells very bad, and we didn't need to analyze it, honestly. We just had to smell the column. It smells very bad. Anyway, so increase in the amount of ammonia was observed. Calculating the chemistry stuff, we were able to know that the amount of calcite that was precipitated inside the treatment area as well. But we are looking for our complex conductivity or geophysical, geoelectrical signal, right? We were able to see a similar trend in here, just like the previous experiment, that we had sort of a no peak sort of thing in the imaginary conductivity signal. And as we started treatment, the peak increased in the magnitude and reached to a maximum level, and then went down and reached to a plateau. Similar, very, very interesting, very similar to the previous experiment, but this time we reached a much higher magnitude compared to the previous step. So we had much more surface area produced by these microbes. Basically, they distributed everything much better than the previous experiment. And then we had the same trend compared to the previous one. So basically increasing, reaching to a peak, decreasing, meaning that the calcite crystals firstly formed as a powder and were scattered all over. And then as we kept injecting food for these microbes and calcium for these microbes, they basically produced larger calcite crystals that they coagulated together and layered together. And basically that initial big surface area, because of the powder form, was reduced into chunks of calcite. So the magnitude signal was decreased. We were also able to see that the peak is not only increasing in magnitude, but also is decreasing in frequency. this is very interesting because it allows us to calculate basically the size of the grains that we have. If you remember from here, for instance, so when the ions want to distribute around this grain, they need a time. Now, if that grain is big, it takes them more time. If that grain is small, it takes them less time. Now, if we can actually measure this with the complex conductivity method as a multi-frequency method, because we have this, we can convert frequency to time, right? Now, initially, it took them shorter times or larger frequencies, basically a smaller precipitates or powder, finer, right? And then as we kept injecting, they coagulated and produced larger crystals. So it took them more time, the ions, to get redistributed. So we were able actually to show that the calcite crystals are increasing in size with this geoelectrical measurement that we were unable to show with the shear wave velocity, for instance. Taking out the real conductivity just to show you that complex, the imaginary part is sensitive to the pore size distribution, surface area, grain size, and so on. And this one is only, the real conductivity is only a measure of solution conductivity and porosity and so on. We can clearly see that there is no such peaks to tell us about the grain sizes or pore sizes in the electrical conduction that is happening through the pore filling fluids at all. So we certainly need to use the complex conductivity methods or the induced polarization technique if we are trying to monitor solid sterilization in the field in the future. So to show that, basically summarize what happened in here is basically we had a soil devoid of any calcite, and then the moment the microbes were introduced with urea and calcium-rich solution, they produced a fine precipitation around the pores and inside the pores, and it reached to a moment that we had a lot of fine precipitates inside the pores, and as time went by, they kind of coagulated together and they kind of clogged the pores. So we don't have that initial increased surface area anymore. So the signal initially goes up, showing we are at the fine precipitation stage, and then it goes down, meaning that we are reaching to a coagulation and layering stage, and eventually reaches to a plateau, telling us that we have done enough and it's right time to stop injecting more material into the soil. Just to emphasize that the microbes produced a more homogeneous distribution compared to abiotic calcite precipitation, we replicated everything at the bottom of a beaker, and we are clearly seeing, using only chemicals for this precipitation, everything starts to coagulate initially, and we are seeing like empty spots. This is not a good distribution of calcite precipitation at the bottom of a beaker. This is exactly the same thing that is happening inside our soil if we're doing this in the field or in our column in the lab. Using microbes, on the other hand, you can clearly see the precipitates are homogeneously distributed. We have almost no empty spot like this one. This one, I don't consider it. Probably it's just a crack or something. But comparing this to the just using chemicals, we can clearly see how more beneficial is to use microbes. They carry the calcite with themselves, the calcium with themselves. They precipitate it everywhere at the same rate. All right, so we were able to show that everything works in the lab. We are clearly able to treat the soil and take the loose sample, convert it into a stiff rock column like this that you can see in this image. But let's see, does it work in the field too? A lot of people have tried to show that calcite precipitation using microbes work in the field, but most of them actually had to take an actual sample like this column and analyze it in the lab to show, oh, this method works, or doing it in a larger pilot experiment in a tank or something. No one has used geophysics to just pinpoint map exactly where the MICP is occurring, how effective that is, and so on. So this is what we want to show in here. To do that, we went to a field site in Rifle, city of Rifle in Colorado, United States. It was a Department of Energy site that previously has shown that microbes capable of decomposing urea exist in the groundwater. So all we had to do is basically feed them with calcium and basically start producing calcite in subsurface. And that made it the perfect site for us. As additionally, that site had numerous well bores already in place, so we didn't have to for ground truthing. So all we needed was just basically take samples from these boreholes, either solution samples or actual samples. So this is a perfect site for us, and it was large enough. It was about 20 meters this side and about 10 meters this side. So I would say large enough compared to a column experiment in the lab. What we did, we used, we know the groundwater direction in here. The groundwater direction is basically from this side to this side. So we started injecting through wells available around here, and basically groundwater took all the ingredient with itself, and then we withdrew from the wells at the down gradient wells in here to make sure that we are not contaminating the subsurface with too much ammonia. So we injected here, we collected in here, and we basically assumed everything is happening in the middle in here, just like what we had in our columns. For that purpose, we laid out our electrical resistivity and induced polarization array on the surface and on 3 lines in here, and we were able to collect data on daily basis. What we did first, we had to kind of make the microbes proliferated, those that are, we wanted as much microbes as possible in that region for us to produce calcite. So we gave them a source of carbon food that was not urea, so just to grow. This was just basically sugar, molasses. We waited 24 hours for them to proliferate and then started injecting urea on daily basis. Initially, we injected with a small concentration. That was not as effective. And then after 8 days, we decided to increase the concentration of urea. So we kind of increased the calcite precipitation much more because we didn't have enough time to stay in that field. We only had 20 days. At the same time, we were measuring resistivity, time domain IP, and a spectral IP, which will give us complex conductivity. So we had like every geophysical method, geoelectrical method over there. Additionally, we had the shear wave velocity measurements in the boreholes that were provided to us. So we had the ground truthing ability with the shear wave velocity. And we also collected all the chemicals in the effluent, such as to analyze a lot of different stuff such as ammonia, pH, conductivity, and so on. So if I want to schematically show what we did, this was the smaller tank in here at top and the larger tank at the bottom in here, and the groundwater is going to the south direction. We injected everything through 3 boreholes from here, and we threw everything from 2 boreholes from down gradient wells and assumed everything is occurring in between these green and red boreholes. We used a SIP 256C instrument from Radig Research Germany for measuring complex conductivity. We used an IRIS Tiscal Pro capable of doing resistivity and time domain measurements at around 4 Hertz for our time domain and resistivity measurements. And we did everything on 3 lines for the time domain measurements and 2 lines for the SIP measurements. Now, why we did use only 2 lines for the SIP is because lower frequency measurements take forever. They take, if you go to the frequencies below 0.1, it can take up to 40 minutes and up for just a single frequency measurement. So we don't have that luxury in the field, right? We went all the way to 0.156, and that took us for the whole measurement from 0.156 to 500 hertz, about 4 hours. And then during that time, you have to do nothing. So you have to just let the instrument take. So 4 hours for one line, another 4 hours for two lines, that's already 8 hours. And then we had to do resistivity and time domain measurements, which took about 40 minutes each as well. So just imagine that we couldn't do it more than that. Anyway, so we had our SIP measurements at two lines close to injection and in the middle, and we assumed because by now everything was precipitated, we didn't use a third line in here at all. But because time domain measurements of IP and resistivity are faster, we did three. So one close to the injection port, one in the middle, and one to the port that we have the withdrawal, to make sure we kind of map everything. We have a 3D grid sort of thing to map everything that is occurring in the subsurface in here. What we did was basically, as you remember, I said the real conductivity or the resistivity is sensitive to the changes to the electrical conduction through the pore filling fluid. So what we did, we withdrew water, groundwater, from these two wells that are outside of our treatment area. We didn't use this one. These wells that are outside of our treatment area, and mixed it with the ingredients that we had and injected back into the treatment area. We did that because we did not want to increase the conductivity that much, and we did not increase it that much. Adding a little bit of urea and calcium, we didn't add calcium. Adding a little bit of urea did not change anything, and calcium already was in the aquifer, so we didn't need to do that. So we kind of made sure that the resistivity part that is sensitive to the changes in electrical conductivity of the solution doesn't change that much. And we are only interested in seeing the precipitated calcite, the change in surface area because of the calcite precipitation. We, at the end of this 21-day sort of thing, 16-day experiments that we had done, the first week was not really good. We were able to see that the calcite was precipitated in our samples. What we did, we basically made soil columns and put them down in this wellbore in the middle. So we had this wellbore in here. So we put that soil sample down there kind of as our core. Instead of taking out a core that we couldn't do it there, it was super expensive, we made a core and put it down. And it didn't have any calcite in it. It was basically sand. And we were able to see after the treatment, we are seeing evidence of calcite in there. So our microbes were able to produce calcite. Additionally, geochemical analysis on concentration of ammonia showed an increasing trend over time, meaning that the microbes actually decomposed the urea as well. We were lucky to do a nuclear magnetic resonance image, the signal as well. I'm not going to talk about it that much, but it's a geophysical measurement that is sensitive to the hydrogen atoms. So let's say you have, the more water you have, the more hydrogen atoms you have, or hydrocarbon, for instance, if you have, the higher the signal. Now, we are doing our treatment in a saturated groundwater environment. So we have all the water we need. If we precipitate calcite in there, we are pushing out the water and replacing it with a solid material that doesn't have hydrogen in it. So what we are expecting is after this treatment, we are reducing the number of hydrogen atoms, thus reducing the NMR or nuclear magnetic signal. And that was exactly what we saw. After 7 days, we were able to see that the signal in the well, in the middle of the treatment area, right between this red and green, has an almost 1 order of magnitude less hydraulic conductivity magnitude measured from NMR compared to these wells outside of the treatment area. That means that a lot of water has been pushed out and been replaced by solid particles of calcite. This is great. This is showing us, okay, something is happening. Additionally, our shiver velocity increased by 40% during this experiment in all directions. So this is our treatment area. We had our source in the middle and then receivers in all of these 3 boreholes, and showed that all of them we are seeing about 40% increase in shiver velocity. So similar to lab, that means something solid has happened and been acting as a cementation agent inside there. But unlike these, I would say one-dimensional data analysis that we did, the geoelectrical stuff are not easy to work with. Initially, I spent a lot of time to clear up the noise. Induced polarization data usually have a lot of noise, and it's not an easy thing to work with. To do so, I and my colleagues developed a software called Recipe that is capable of doing a lot of data cleaning for you that I recommend if you're using geoelectrical in your field, use that software. I learned these, I would say, the hard way, how to deal with my data, because initially I wasn't seeing any signal. So what I did was I collected data, I did some initial filtering, some stuff that made no sense were completely removed, did error analysis and applied that error on my data, and then finally filtered the data after the error analysis and did inversion. I'm not going to go over the process of inversion, how it works, but basically it will compare your data to a known model and try to find the lower misfit and gives you the a resemblance of what's happening in the subsurface. To do that, I use a software called, I use the software that we developed, Recipe, right? So in here, I'm just going to show you how it worked. Basically, what filters are available. You can, if you have reciprocal data sets, for instance, you can clear your data from obvious errors. If you have induced polarization, you can basically filter them based on range, or you have nested measurements, meaning the potentials in between currents. You can remove that as well. There are a lot of different types of filterings available in the software that I urge you to use them if you ever measure any induced polarization signal, and different error modeling as well. And this software is freely available to download. The source code is also available. So if you want to do some coding, you can also do that. All right. Now, what we did here, we had 3 lines that we measured on electrical resistivity and time domain IP, and 2 lines for spectral IP. We measured the chargeability, that we were able to convert it into phase shift and then take out imaginary conductivity out of that for a time domain signal, because we knew the frequency that the instrument, the IRIS instrument was working, and we easily could compare it to the SIP measurements. We did all these hassle of time domain measurement to show that can we use time domain IP instead of SIP. This takes 40 minutes maximum. This one takes 4 hours at least. So if you're an engineer, you don't have four hours to do your measurement. If this one works fine for you, you're going to take this. Resistivity clearly showed the subsurface structure. Obviously, as we all know, we were able to see everything with resistivity, but it wasn't the right signal for calcite precipitation. I'll show you in the next slide. We were able to see the clay layer that was put in that site as a part of site remediation in 1990s. We were seeing the groundwater region in the porous material with a higher resistivity because that was a fresh water. So electrical resistivity was really good for mapping the structure. And it failed to show calcite precipitation, the resistivity, because if you remember, it's mostly sensitive to the porphyrin fluid conduction. right? And we didn't change that at all because we used groundwater, mix it with a little bit of urea, which doesn't change chemically the conductivity that much, and inject it back into the groundwater. So as you can see, if I use a time-lapse image, basically showing the changes over time, we are seeing that the resistivity is not showing that much changes over time. So calcite precipitation is not basically as effective to increase the resistivity as we expected. We are not injecting so much calcite that basically push out all the water possible. We are injecting a little bit. But imaginary conductivity, on the other hand, was able to show more than 500% change over time. So very sensitive to the precipitation of this fine powdered calcite inside our soil. So this is technically the right method to go with. You need to measure induced polarization to be able to get the imaginary conductivity to measure if your MICP is working. Resistivity alone won't work. So we are in the field. We don't have time to do all those calculations of imaginary conductivity, but we are measuring the phase shift and the impedance. So let's see if the phase shift alone without conversions and everything to calculate the imaginary conductivity works or not. We already knew that the imaginary conductivity works from the previous slide, for instance. But let's see if the phase works as well. Or let's say the field measurements of our complex conductivity. Clearly, as you can see, over time, the line that was closer to the injection port is showing an evidence of signal increase, matching the treatment area that we had. So the phase has actually increased over time, all the way to around 6 milliradians. And bear in mind, we use phase as negative value because it takes time to measure it. Right? It's like a negative value compared to the actual time. It's a delay, so it's a negative. For the second line, the same thing happens. The start was a bit delayed, I would say. And then, as you can see again, by the end of the experiment, we are clearly seeing the changes in the treatment area. And the third line, we didn't have a background measurement for that because we didn't have a third line initially. Again, time consuming, right? So, but then decided to add it. So as you can see, we are seeing the same kind of effect, but maybe a smaller compared to the two, at least in the area. So I would say all of the precipitation sort of occurred closer to injection in the middle, and then there was nothing left for the last part. Nothing but smaller amount. If we show that in a three-dimensional sort of thing and exclude all the surrounding, you can clearly see the calcite precipitation occurring exactly where we want it to happen. And our geophysical phase shift measurement basically is similar to the imaginary conductivity, assuming that the real conductivity, which is because of the water conductivity hasn't changed, remains constant, is sort of the same thing. We are seeing that we are clearly mapping the subsurface affected by MICP. And as you can clearly see here, we are also seeing in the direction of the groundwater, we are seeing more precipitation. So our geophysical technique is much more effective to map the subsurface affected by MICP than direct sampling, such as shear wave velocity, I would say, and a lot of other methods. All you need in future is just a small amount of measurement showing that the MICP actually worked. And that could be like an effluent sample or something, and the rest is by geophysics. You can install these electrodes permanently on the site, do your measurement, and basically enjoy. Our SIP measurements were similar to time domain. The real part of the spectral IP did not show any changes over time, only showed the structure of the subsurface as expected because we didn't change any conductivity. So over time, we're not seeing anything. But if you use the phase shift and basically do a time-lapse analysis, we are clearly seeing at the same area the increase in the signal is observed at higher frequency as well as lower frequency. So we are seeing a difference in here. So the peak of the signal at higher frequency is different than the lower frequency. that could be because of a lot of different things. Microbes can affect at different times, right? And at different times that can affect, be measured at different frequencies and so on. So we are still sort of investigating why this has happened. These are not basically exactly the same, but basically that can be because of a lot of different factors in subsurface. Nonetheless, both of these at different frequencies, we are clearly able to see the changes in the subsurface with the spectral IP. But one would say, okay, this took you 4 hours for each measurement, so it's not as beneficial. Your time domain IP clearly was enough because you were able to see the changes in subsurface with that too. So if I'm an engineer, I would go with time domain for my field measurements. So in conclusion, MICP improved the soil stiffness. So it's the method to go if you want to do soil stiffness as an environmentally friendly approach. The phase anomaly respond to MICP precipitation clearly showed the direction of the groundwater and the precipitation area. All of the geophysical methods are sensitive to the changes during MICP, but time domain and SIP, time domain IP and SIP are spatially and temporally more sensitive compared to the other methods. And SIP is sensitive to calcite precipitation pattern because we saw that we can detect the fine precipitation compared to coagulated precipitation. But because it's time domain, because it's so time consuming, probably an engineer only prefers to go with the time domain in the field. Now, I also have, I can also talk about the deformation, the second part, but I'm not sure if I have time. So I don't know, if you want, I can do that, but if you don't want, I'm gonna stop here, so. Do we have time?
Yes, you can continue.
Okay. All right. So yeah, this is more interesting, honestly, to me. I would say, because a lot of engineers actually use a lot of. There is no indirect method to measure the deformation and so on. So let's talk about this. What is soil deformation? Basically, if you apply a stress on a column of soil, for instance, or any type of soil, it will deform. If that stress is not too much, that deformation is gonna go back because all the soil act is elastic. So if you apply a little load, it will deform, but if you remove that load, the soil will go to its back form as long as you're not applying more than what it can handle. If you apply more than what it can handle, initially it will permanently deform. So we call it a plastic deformation. So for instance, if you have a column, apply too much load on it, it will become like a barrel. And if it's even too much more, it eventually will fail. What happens, there is a shear failure or a fracture forming in our soil column. The same thing happens on the field scale on the ground. So all those landslides that you're seeing, or because the load was more than what the soil could handle, or basically remove the resistance by too much water, maybe precipitation of too much water from the rain, for instance, and then soil fails on its shear plane. That's why most of the landslides have like a side of thing, like a wall sort of thing. That's the shear fracture. We can quantify this deformation in the lab with confined compression or unconfined compression test. In here, I'm just going to go with the unconfined, for instance. What we do, we gradually increase the load or the stress on the soil and measure the changes in its length. If we plot this, we will have a linear part which will tell us the elastic region. When we remove basically it tells you if you remove the load, you will get to retain the same shape initially that your column had. But if you increase the load, we will get to a nonlinear part, which is the plastic form. And essentially, when the soil cannot handle more stress, it will fail on its fracture plane and start sliding on this. And the only thing that keeping the slide from to be an instant thing is because there is a friction in this plane as well. So that's why we see a sharp drop at the failure point. This is basically after that, all remaining is a residual strength. That's the only thing that's happening is the friction on the fracture plane. We will do that in the lab by an instrument called a triaxial instrument. Usually we have a load frame that will apply a very small stress on the sample over time and basically push it so it compresses it. We will measure the changes in the length by a strain transducer. We will measure the amount of stress by a load cell that we have. And if we want to do a triaxial measurement, we need confining stress as well. We can fill up the sample holder with water and measure that as well. Well, in here, we didn't use that. Just a recap on complex conductivity. So you measure the polarization and also the conduction at the surface and the conduction at the electrolytic conduction through the pore filling fluid. So in here, again, if you have pore spaces getting smaller because of the compression, for instance, the ions can travel in a shorter time, so you would have a different signal than the initial time. So it's important to use complex conductivity. Now, the thing is to have electrodes on your samples in here, you need to create a customized sample holder. Most of the civil engineers don't have electrodes on their sample holder, so it's a unique, uniform column of soil. But what we had to do is basically make that uniform sample holder capable of holding electrodes. So we 3D printed this material and then created this elastic sort of flexible sample holder. The designs and everything are available publicly. You can look at that, the publications that I have at the end. So you can do that on your own if you want. Well, it made us to do basically kind of combining compressive strength test with the complex conductivity. So at the same time, we were measuring the SIP signal, the complex conductivity, and the compressive response. So we kind of simultaneously were measuring this and our complex conductivity at the same time, and kind of were able to correlate these two together. Our finished sample holder will look something like this. In the civil engineer part, we don't have these electrode holders, and it's just a uniform column. We had a soil sample that had 250 to 300 micrometers silica sand, 98%. We added 2% kaolite powder in there as well, because we need a more sort of a stiff column, and whatever it could actually hold on together to be able, because if you only have sand, it wouldn't hold, it would just collapse when you partially saturate it. We partially saturated that below its liquid limit, so we would know this column would stand on its own, as you can see in this image. And then what we did was we basically compressed the sample very slowly at the 0.0001 millimeter per minute. We measured the effluent volume from these ports, stress, the strain, and at the same time we did the complex conductivity measurements. We were able to show at both high and low frequencies that the surface imaginary conductivity is very sensitive to the increase in the stress as well as the failure. But we couldn't see the same thing for the real conductivity part, because even though we were pushing out the level of solution, right, but it is insensitive to the compression, basically, of those pores becoming smaller or larger. It is not all time insensitive. It's small sensitivity, because we are changing the process, right? But we can see that the imaginary part is much more sensitive, basically tracking the same sort of behavior. Our signal initially had a linear part, became nonlinear, and eventually failed our sample. And we can clearly see that in our imaginary conductivity signal as well. Very similar, although there are some noise, but the overall trend is very similar. To show that on our phase signal, which is good for field measurements, we can clearly see that as well. Initially, we have a peak at below 1 hertz, it increases in the magnitude, and then at the failure point, it immediately decreases. And also, we are clearly seeing a trend from lower frequency to higher frequency. So that means that our pores are getting smaller. So the time constant is going towards higher times. If we just plot the time constant, the relaxation time constant, basically the time that takes the ions to diffuse back when they are polarized, we can see that they are reducing over time. It shows you that we have compressed the sample and reduced the pore sizes. Initially, they were whatever microns, and now they are much smaller because of the compression. So our imaginary conductivity and phase shift and basically the complex conductivity was capable of showing the soil failure. The soil failure clearly occurred in our samples. I pushed this far beyond its failure point. You can clearly see the fracture inside the column. Our initial failure occurred at much smaller value than this one that you can see in here. But just to visualize it, you can clearly see the same kind of a fracture I showed you initially. Schematically. We did another experiment, this time just to measure the deformation. So we had a soil sample that didn't show that much of a failure like the other one, that sharp drop, but kept showing some peaks and up and downs in the stress signal. And you can clearly see that the imaginary conductivity also changes at both low and high frequencies with the same sort of peaks, like inverse of the peaks of we are seeing in here. This is interesting. It shows you that not only we are able to show the failure, we also show any rearrangement of the grain during this compression. So you can have this complex conductivity method in the field, and any changes that are occurring, you can see it in the signal. You don't have to go there and take an actual sample, do a stress analysis, so on and so forth. All you have to do is basically a few electrodes on the surface, and anything that occurs, you can basically see it. It is very good to be used in future if you want to predict soil failure, right? The saturation and the electrolytic conductivity changes were unable to show any changes, unlike the imaginary conductivity as expected, or as we talked about. So basically, we are with complex conductivity able to show the soil failure. Now, if we use that signal, we see kind of a flattening in here. This is a good indicator for the future studies. If we reach this flat point in our signal, we could say, okay, soil failure is near, be careful. And that's basically what I have in mind in future, that our studies, if anyone wants to join my group at the University of Oklahoma, it's the next step. We are trying to show that deformation is measurable with the electrical methods. And old methods are not good anymore because there are a lot of wires and so on. So we can procure new instruments that they don't have any more cables and so on and so forth. And they use, each of the instruments use a Raspberry Pi and do the analysis on the go. And with having the capability of using, for instance, 5G network, that is a hot topic these days, we can do all the analysis on the go with machine learning and so on and predict soil failure, basically when the signal gets to that flat point. What we can do is simply at this point say, okay, that environment is no longer safe to live on or do any constructions. So all in all, we will be able to use this to predict any kind of disaster that may be happening. And so with that, I hope you enjoyed the talk. I tried to cover a lot of things. I know I hope it was educational enough. And if you have any questions, I'd be happy to answer.
Okay, thank you very much, Dr. Sina, for very interesting talk. Now we are going to the question and answer session. So to all participants, if you have any questions, please write down to the chat box or you can raise your hand to ask directly. There is one question from Mas Irfan Prasetyo. Can you see in the chat box, Dr. Sina?
You're welcome. I'm interested. Did you perform seismic borehole question also during data collection? Yes, that's what we did. Basically, the shear wave velocity or seismic borehole. That was all it was. We didn't do compression wave though. We only had the seismic, the shear wave. Yeah. So we had it hammer down the borehole, sort of pull the cable, and then there was the hammer smacking down the borehole.
Okay, I think the answer is enough, Mas Irfan. So we continue to the next question from Mas Bomer Lumbon Torwan. Can you see in the chat box?
Yeah, so they say, thank you for your course, Mr. Sina. I'm curious about the bioagent method. Can this method be used for slope stabilization in mining slopes? Maybe. And are there conditions that can cause the bacteria to die while the method is applied? Yes, yes, very important thing. The microbes need a very, very specific pH range. They only survive between 8.6 or 9, something like that, to 9.5. So if the environment becomes super basic, like more than 9.5, they die. If it becomes acidic, lower than 8.5 or even lower than 7, they die. So you have to maintain that pH. It's easy to do in the lab. It's not easy in the field, but pH is very important. For the first part that can be used for the slope stabilization mines, probably, but I haven't tried it yet. It's a good research project probably in the future to show that. So that's a good point. The next question says, thank you, you're welcome. I want to ask you, what are the effects and empirical relationships between microbial processes on the geophysical properties of the shallow subsurface? I don't think anyone has actually developed any empirical relationships to that end yet. Most of the work that has been done was experimental, showing we are seeing a signal, and no one has correlated the magnitude of the signal, for instance, to the amount of precipitation yet, and no one has done any modeling yet. And that's one of the, I would say, downsides of my work, because I haven't done that yet. But it's very important to kind of do some modeling and get that empirical relationships out. So again, that's a work that should be done in the future. So far, we just show that experimentally we can see something consistently. So, but how it works, we don't know. Why it works, we are assuming. Yeah.
Okay, one more question from Ms. Rifa Salma Salsabila. Can you see in the chat box?
Yeah,
Mr. Irfan Prasetyo.
Oh, I didn't see that. Sorry. Thank you, Sina. This is the topic. How can we identify the porosity, permeability, resistivity, and also the connectivity using shear velocity? We can't that easily. Not that I know of. I don't think you can do permeability. Maybe. I haven't tried it. I'm not a seismic person, so I'm not the right person to ask me about this stuff. I know from resistivity and induced position, you can do all of them, porosity, permeability, and it's easy. But you clearly can't do resistivity from shear velocity. That's not possible. I'm not sure about porosity and permeability, so I won't comment on that. But with electrical methods, that are the methods to go to do all of these that you asked.
Okay, thank you for the answer. I think there is no question again from the participant. If there is no question again, we can end this session, but before that, we have the photo session, virtual photo session.
What?
So thank you very much, Dr. Sina Senyang, for the very interesting and useful lecturer. So now we are going to the photo session. Miss Riva, can you help me? Before that, Bapak Dr. Wahyudi, do you have something to say? Please.
Yeah, thank you, Sina, for your interesting talk, and we are happy with that. Yeah, this is relative new for us, new for us. Your material is new for us, so yeah. In our laboratory, we will conduct such a test. Yeah, but we have problem during this pandemic time.
Yeah.
So yeah, maybe in the next time I will ask you more through email or so. Yeah, and on behalf of our Department of Geophysical Engineering, we thank you very much for your lecture. Yeah, this is helpful for us. Okay, thank you.
Thanks for the invitation. All right, have a good one. Goodbye.
Bye. Yeah, now photo session first.
I don't know what that is. Am I supposed to be that photo session?
You should join us.
Okay. Okay.
We're waiting for Mbak Riva. Please.
Okay, to all participants and Mr. Sina, can you open the camera and we will start to open the photo session.
Camera is open.
Okay, wait. Keep smile to all participants so we can get the best picture. Now for first slide, 1, 2, 3. And then second slide. 1, 2, 3. And then the third slide. 1, 2, 3. And then the fourth slide. 1, 2, 3. And the last slide. 1, 2, 3. Okay, then. Thank you to all.
All right. Send me the picture.
Thank you, Miss
Okay,
Riva.
yes. We will.
Yeah, thank you very much.
Thank you,
All right.
Dr.
Thank you,
Sina.
Sina. Yeah,
Thank
and
you.
Yes.
thank you for all attendance. We see you again tomorrow.
Yes.
Thank you. And now I end this session. Thank you.